Happy day, students. So let us start today a new topic called diffraction. Okay. It is another property that is exhibited by wave nature of light. Okay. But is it a property only of light or for all type of waves? All type of waves. Okay. Mechanical as well as non-mechanical. Both waves exhibit diffraction. So let's understand first what do we mean by diffraction. What is the meaning of diffraction? Actually, a process in which the wave bends from its path due to obstacles or openings, or you can say openings like a slit that we have studied in interference. Okay, a gap, a hole. Okay, so bending of the wave through obstacle, hole. Okay, we will call them as diffraction. Okay. If we talk about sound, we observe it on a daily basis. How can we say that? At home we have observed that if we are going to produce a sound from one room, your brother, your sister or your parents are sitting in another room. When you are going to call them, they all will come to you. So how the sound has reached to another room? Because normally we know that the energy travels in straight line. Correct or not? But it has moved to the other room also. From the door it has gone, or from the opening it has gone to the other room. Okay, so definitely there is bending of the sound is taking place. If I say an example, if suppose we take, there is a road over here. This is the road, and you are standing here. Okay, and consider these are actually walls. This is also a wall, and here some car is coming, and car is producing a sound. Okay, car is producing a sound. So this sound now, if I am going to follow the Huygens wave theory, and if I take this as wave front over here, so if I make a wave front like this, now it's not going in this direction because these are obstructions. So it's coming like this, but over here, what will happen? Okay, is it reaching you? Yes, it's reaching. So that's how the sound is coming. And if you see, if this is the source, then if we take straight line, it should have come like this. But has it come like this? Answer is no. How it was coming? Till this point was coming like this. This point was coming like this. So from here then, again, it has produced its own wavefront, secondary wavelets, which are going like that. Okay? And you got the sound. Are you able to understand? So this is how we are saying the sound is bending. Sometimes in the classrooms also, because of some punishment, you are standing outside the class and your teacher is teaching inside. So do we get the sound? Answer is yes. So that is because of the bending of sound, and that process is called diffraction. Okay. But when we talk about light, we do not observe that the light bends. In all the circumstances, we have seen that light travels in straight line. So then how can we say that light also diffracts? The reason for that is that we observe that sound diffracts and the light doesn't. The reason for that is what? There are two parameters which decide the extent to which diffraction takes place. What are those two parameters? Let's see. Two parameters. So what are those two parameters? One, the size of obstacle or size of opening or hole through which the light is passing. Okay. Second thing is wavelength of wave. Wavelength of waves. Okay. Now if suppose that there is obstacle, let's say this is the obstacle, and this is how the wave is coming, or the sound is coming, or the light is coming. This is the size. Let's say that's A. Okay. Or if you say that there is a hole over here through which the light is passing or the sound is passing. So this is the size. Okay. So if this A is comparable to wavelength of the wave, then we will observe the diffraction. Okay. If it's smaller than wavelength, definitely we will observe, but at the most it should be comparable. If it's comparable, we will be able to observe the diffraction process. Let's see then in sound what is happening. We'll find the wavelength of sound and we'll try to find out what should be the size of the obstacles or openings so that diffraction we are able to observe in case of sound. Okay. If we talk about sound, the speed of sound we know is 330 meter per second, and the frequency of sound that we hear ranges from 2 to 20 to 20,000 hertz. Okay, now let's see what wavelength is possible in the two cases over here. So wavelength, it can be V by M, that's the formula. So 330 by 20 to 330 by 20,000. Okay, so what value we are getting? 33 by 2. 33 by 2, 16.5 meter. 16.5 meter. Here, this gets cancelled here. This is 33 by 2000. Now this is in meter. Let's convert this in centimeters. So 100 more over here. This gets cancelled. Is 33 by 20. Okay, that means 1.65. So 1.65 centimeter to 1.65 meter is the wavelength of sound. So if the obstruction is of this size, 1.65 centimeter, that means it's considerable, up to this much. 16.5 meter is huge. So if this is the size of the opening or obstacle, even then we can observe the diffraction of sound. If this is the size like this, even then we are going to observe the diffraction of sound. Now these kinds of obstacles, these kinds of openings, they are all around us because we are able to see them also. That's why sound diffraction we can observe or notice very easily. But it is very tough as far as light is concerned. Why that? Because we know that when we talk about visible spectrum of light, its wavelength is from 4,000 to 7,000 angstrom. 4,000 angstrom to 7,000 angstrom. Now 4,000 angstrom means what? 4 into 10 to the power minus 7 meter. That means 4 into 10 to the power minus 4 millimeter. Now this size of obstacle, this size of opening, we cannot see also. Okay, so since it's very small, that's why it appears to us that the light is always traveling in straight lines without any diffraction, without any bending. So if at all we have to see the diffraction in light, we have to create or we have to make an experimental setup. In that one only we can observe the diffraction. Reason? Because the wavelength of light is very small. Whereas sound, we are observing it on daily basis. Okay? So diffraction again is what? Bending of light through sharp edges, through small openings. Okay? And when we are going to see it in a predominant way or observable way, when the size of opening is equal to the wavelength of the wave. Okay? Now let's see then. Here we are going to study diffraction in light. Okay. So in light, Grimaldi was the person who observed the diffraction first. Okay. But it was explained by Fresnel. It is explained by Fresnel. So whatever we are going to study, that is the theory or explanation by Fresnel only. So what he said, that I will explain it first. Okay. So if suppose we are going to take one opening, something like this. This is the opening, okay, and this is the size of the opening. From here, if I say one plane wavefront is coming, like this. Okay, and in this rays, these light rays, if I make plane wavefront, they are like this. This is plane wavefront. Okay. And I can assume that the separation between the two wavefronts is actually equal to wavelength of light. Okay. Now you can see in this case, I have taken the opening A is a lot greater than lambda. Lambda is this much, whereas opening is this much. So it's a lot greater. So what will happen? In this one, the diffraction that we are going to observe will be very small. So what will happen here? This is a plane wavefront. Check it over here. This plane wavefront will come here like this. Okay, but what will happen due to this point over here, this point, which is also a part of this wavefront and which is also doing the SHM. So because of this, a light will tilt a little, something like this will happen. Okay, this is a part of this. This is a part of the same way here also. Okay, so how much is the bending over here? Bending will be very small, like this. Where we can see this, if suppose here is a screen, then we know that in this region obviously the light should come because this is the opening. But what we observe is here also some part of light is. Okay, so bending is happening here also when A is very large as to lambda, but its extent is very, very small. If I am going to make it even smaller, very, very small, then see what happens. If the opening is very small, this is the opening. Can you see that? Now, if we take the rays over here, okay, something like this. These are plane wavefronts. So in this case, what I have done is the A, the side, this side, I have made it very, very small. A is even smaller than lambda, and here is the screen. What's going to happen? Just check. Now here I can find one particle which is going to oscillate because of the energy which is coming like this. Now this is a particle, single particle I have made. Now because of this, how the wavefront will go? Okay, going in this. So how the diffraction is happening? Check. Are you able to see? Can you see the bending? A huge bending as compared to the previous case. Okay, in the previous case, more light was moving in a straight line. Very, very small amount of light actually bended, but here the light is bending to large extent. So this entire area here on the screen will have light. Okay, but this area will have the maximum light. Okay, because this is the size of the opening itself, so this will be the brightest. But other areas also will be getting light. Okay, so this is diffraction. Are you able to understand? Now one more thing is there. What should be the, on this screen when this light is going, is the intensity throughout same or different? Intensity is different. And in this case also, there is going to be interference. Interference of different waves. Okay, you see that I will show you now. So on the screen, Fresnel observed different type of intensities. There was also maxima, there was also minima. Okay, so what's happening, I will show you. Suppose this is the opening, and in this one I take two particles over here like this. Okay, so if you make the wavelets because of them, these are the wavelets. Okay, and on this wavelets also I can make one particle, let's say two particles, third particle and fourth particle. And I make their own wavelets. So how they will come? Like this, like this, like this, and like this. Now, if I am going to make the rays because of them, because rays will always be perpendicular to wavefronts, it will be going like that. This will be going in this way. Okay, this one and this one. So you can see that they are actually going to interfere. If I am going to take more over here, more particles, you can see that these will be interfering. But interference will not take place in this area. This will be the brightest. Okay, because here the light is coming directly over here. Which light is going in other directions, there they are going to interfere, and we are going to get the dark fringes and bright fringes because of that. But none of the bright fringes will have same intensity as that of the central ones. Okay, because light do travel in straight line. A portion of light only is getting bent, okay, or getting diffracted. Are you able to understand? So this is also going to interfere. So this interference is of what? Secondary wavelengths. Interference of secondary wavelet of same wavefront. Okay, whereas in interference, what we studied in Young's double slit experiment, interference of waves of two different wavefronts. Okay, whereas here the same wavefront, secondary wavelet interference. Okay, that's all for now. Remaining we'll see in the next class.